Okay, are you able to see the slides in full screen?
Yes, we are able to see.
So there is a wide range of algorithms in the area of visibility, which is a sub-area of computational geometry. So in this presentation, we are going to get an introduction to the visibility algorithms. Okay, so what is visibility? So if we have 3 points, let's say in this figure there are 3 points. And I mean, it need not be in the plane, it could be in the 3D space also. For every pair of points, visibility is defined as the existence of a straight line of sight between the 2 points within any without any obstacles. Let me take the pointer. So between P and Q, there is a straight line of sight and there are no obstacles in between. So P is able to see Q. And if P is able to see Q, then Q is able to see P. But between P and Q, there is some opaque obstacle which prevents P from seeing R. So R is not visible from P and vice versa. But Q can see R and vice versa. So let's look at a concrete problem in practice. So suppose you consider an art gallery. So there are artifacts and artworks displayed on the walls of the gallery. And in this case, it's a rectangular floor gallery. So the question is, how do you secure the walls of the art gallery? So how many cameras you need to put to secure the walls of the art gallery? So it's a practical question to ask. So let us first try to formulate it in the language of computational geometry. So we shall represent the art gallery with a polygon. So in this case, you can see there is a complicated polygon. And it's a simple polygon. So what is the definition of a simple polygon? A simple polygon is a polygon such that its boundary is a single cycle. Okay. As you can see, the boundary of this polygon is a single cycle. So in that case, we'll say that this polygon is simple. But this is not a convex polygon. A convex polygon is a polygon where every angle, every internal angle is less than pi, less than 180 degree. But here you can see there are internal angles which are more than 180 degree. Now this is the representation of our art gallery in the language of computational geometry. We have a polygon to guard, which is simple, which is not self-intersecting or does not contain holes. So now in this figure, you see that if there's a camera which is able to rotate 360 degree, or maybe cameras are placed on around this. So there are cameras around this object. So at the same time, 360 degree visibility is there. So this shaded area is what this camera is able to see. So if you place only one camera at this point, then all these white areas are not guarded. Okay, so the polygon is not guarded. That's what we will say. So the question is, how many cameras do we need to guard a simple polygon so that every point in the polygon is visible from at least one camera? So let us be more specific. So let us say that we also define the simple polygon. I mean, we specify the number of vertices of the simple polygon to be n. So we give the description of simple polygon with n being the number of vertices. And then we ask the same question, that how many cameras do we need to guard the simple polygon, such that for every point inside the polygon, there is at least one camera that can see it, so that the entire polygon is guarded. Okay. So that is the question. Is the question clear to everybody? Is there any doubt on the question?
How many minimum number of cameras or?
How many cameras do you need? How? Yeah. So what is the minimum number of cameras do we need? We want to minimize the number of cameras. So it can depend on the complexity of the polygon. So let us say there is an n vertex polygon which is convex. Then only one camera will suffice. For let us say there is a uh, regular n polygon. All the sides are equal. Then that's a convex polygon. And if you put anywhere in the in the interior of the polygon, if you put the camera, then the entire polygon will be visible. So by definition, every point is visible from every other point within a convex polygon. But if the polygon is more complicated, then more cameras might be required. So how many cameras are required uh, for an n vertex polygon also depends on the complexity of the polygon. So one natural way to solve the problem is to observe that every simple polygon can be triangulated like this. So I have added this additional edges which are called diagonals. So in a way such that the diagonals are non-intersecting. Okay, and observe that there's a maximum number of diagonals I can add. So if I add one more diagonal, then there will be some intersection with some existing diagonal. So such a diagonalization of the polygon is called a triangulation. So the triangulation will help us answer these questions that how many cameras will be required. Because once I have done the triangulation, and then if I put one camera within, let us say, this triangle, then I know for a fact that at least the interior of the triangle is entirely visible by this camera, which is within this triangle. Okay. So the question is, how many triangles in a triangulation of a simple polygon? This you can do some trial and error. So a simple polygon of n vertices. So let's say n vertices. So there is a simple polygon, n vertices. The question is, in a triangulation, how many triangles will exist? Any guesses? Try with some quadrilateral followed by pentagon followed by hexagon, and then you will get a pattern.
Sir, I had a doubt.
Yes.
This triangulation is not necessarily unique, right?
Yes, the triangulations could be of different patterns. There could be different triangulations for the same polygon. But the claim is that the number of triangles in any triangulation for a given simple polygon remains the same. So how many triangles in the triangulation of a quadrilateral? So let us put the different values of n and then check how many triangles are there in the triangulation. So let us say we start with n equals 4. So quadrilateral, how many triangles in the triangulation?
2, I guess.
Yes. So here is a quadrilateral, and you can draw only one diagonal because as soon as you draw the other diagonal, then there will be intersection. So 2. So let us say there is a pentagon. How many in a pentagon?
3, I think.
Yes. Very difficult to draw with this pen. So what is the number of triangles in a triangulation of n vertex polygon? Can you extrapolate?
For 6, is it 4?
Yes.
Okay, then I mean it looks simple. I don't know if it's correct or not. Is it n minus 2?
Yes. It's as simple as that. So irrespective of what triangulation you draw, because the triangulation is maximal in nature, the number of triangles are going to be same in the triangulation for an n vertex triangulation, and it is n minus 2. So what does it mean? What is the upper bound of the number of cameras to guard an n vertex simple polygon?
It should be n minus 2.
Right. So it means that yeah. So the number of triangles. Let's take the pointer again. The number of triangles in a triangulation of simple polygon does not depend on the complexity of the polygon. It is n minus 2. And this is the theorem. Every simple polygon admits a triangulation. And any triangulation of a simple polygon with n vertices consists of exactly n minus 2 triangles. And therefore, n minus 2 cameras can guard the polygon. Because if you put for every triangle one camera in the interior, then that triangle is definitely guarded by that camera. So far, so good. Okay, now the question is, can we do better? Can we place less than n by 2, n minus 2 cameras to guard the polygon? Because, for example, if I put a camera here, it not only sees this triangle, it also sees this triangle, this triangle, this triangle, this. So many triangles it can see. So placing one camera each inside every triangle seems an overkill. How about placing camera on some diagonals instead? Diagonals means the additional line segments that we have drawn. These are the diagonals. Can we somehow place cameras with the diagonals in mind? So one more thing. So the number of triangles is n minus 2. And what is the number of diagonals? So for a quadrilateral, one diagonal is sufficient. For a pentagon, 2 diagonals is sufficient. For a hexagon, 3 diagonals is to be drawn. So for n vertex polygon, how many diagonals in the triangulation?
N minus 3.
Right. So you know there are n minus 3 diagonals. Now can you say something about the number of cameras you need by exploiting some property of the diagonal? So if you place the camera on a diagonal, how many triangles are covered for sure?
Two triangles.
Yes. So every diagonal is part of at least two triangles. So this diagonal is taking part in this triangle as well as this triangle. So if I put a camera here, then at least the adjacent two triangles are covered. Maybe more are covered, but adjacent two are definitely covered. So it means that I can put one camera for every two triangle. Okay. So there are n minus two triangles, and I can put one camera for two triangles. So how many cameras are required? Oh, I have written n minus 8, should be n minus 2. Just a second. Yeah, so yeah. Yeah, if we put so for if I manage to select diagonals in such a way that two triangles are covered by one camera on the diagonal, then we can make sure that n minus 2 by 2 cameras will be able to guard a simple polygon. But then can we do better? So how about placing cameras uh, on some vertices? The vertices are even better. Like for example, this vertex is able to cover all the triangles that are originating or that are incident on this vertex. So this vertex has how many incident triangles? 1, 2, 3, 4. Okay, this vertex has so many incident triangles. So if I put a camera here, so many things can get covered at a time. So it looks like that even n minus 2 by 2 is not tight. We can get the job done with fewer number of cameras. So give it a thought for a minute.
So we have to find a vertex where maximum number of triangles like share the same
Yes,
vertex.
yes. So we can to be greedy. We can say that look, let's find that vertex on which many triangles are incident. So for every vertex, we can keep track of how many triangles are incident to it. And then we can run an algorithm. But then we have to make updates. For example, in this case, it looks like that this vertex is the greatest. This vertex is the best to pick for putting camera. Then I can cover 1, 2, 3, 4, 5, 6 triangles for sure. But then once this triangle is taken care of, I have to update the value of the number of cameras triangles being covered by this vertex, because this triangle is common to both this vertex and this vertex. And similarly, so means, but then the updates are also sort of to the adjacent vertices only. So now something can be done. Some exploitation can be done. Good observation. But can we do something else? So it turns out, anybody has any suggestions? Otherwise, I'll suggest something. So it turns out that if you look at the graph consisting of the edges of the polygon and the diagonals. So this is the graph. The vertices are the vertices, and the edges of the graph are diagonals as well as the sides of the polygon. Then this graph is three colorable. So three colorable in a specific sense. So three colorable in the sense that for every triangle, you pick three different colors for its vertices. So it is possible to draw the vertices of this graph such that for every triangle, there are three distinct colors for the three distinct vertices. Okay, so what can we say now? So for every triangle, how many vertices you have to pick?
One vertex.
One vertex is sufficient. Now, how many triangles are there? So only n minus 2 triangles are there. So n minus 2 by 3 is sufficient. Okay, so therefore there is the theorem, which is the first part of the art-gallery theorem, that n by 3 cameras are always sufficient. Oh, so where will you put the cameras? You can put the cameras. You can choose one of the colors. So here there's black, there's white and gray. So let us say there are the least number of so let us say out of these three colors, white has the least number of vertices. Then you will place cameras at the white vertices. And you know that all the triangles contains at least one white vertex. So all the triangles get covered. Is that fine? So the proof of why this is three colorable, that comes from the fact that the dual graph of this triangulation is a tree. So what is a dual graph? For every triangle, you take a vertex. And if two triangles are adjacent, you take edge. You take an edge, you draw an edge. So that graph transfers to a triangle, and that property enables us to prove that that there is a three coloring of this triangulated polygon. So now the question is, can we do better? Can we use even smaller number of cameras so that the simple polygon is guarded? Yeah, so that is the question.
Sir, can't we combine triangles to form larger convex shapes?
You mean you're suggesting some strategy to bring the number of cameras down from n by 3?
Yes, something like that.
Okay. So you're saying that there could be some strategy. So I think I suppose that because you see that. So for example, this white vertex, we are saying that, okay, this white vertex is responsible for this triangle, this triangle, this triangle, and this triangle. But additionally, this white vertex is also responsible for this triangle, which we are not capturing. We are taking another white vertex. So you're saying that why can't we capture all the triangles that are visible from a vertex? Is that the rationale behind your thought?
Sir, but I was also taking care of the fact that when we are combining triangles, we always form convex shapes. So the example you chose, it won't necessarily be convex.
So you want to focus on only convex portions of the polygon which are visible from vertex.
Yes, sir.
I don't know if that will work. I don't know if that will work. But this is only the first part of the art-gallery theorem. So the second part of the art-gallery theorem says that we cannot do better. So there are some cases where we cannot do any better than n/3 floor. So n/3 floor cameras are occasionally necessary to guard a simple polygon on n vertices. For example, look at this picture. So here is a polygon. So it's like a comb-shaped polygon, comb-shaped polygon. So these are the teeth of the comb. So they're saying prongs. So there are n/3 by floor prongs. Okay. So if this is 1, so how many vertices? 1, 2, 3. This is 2, 3, and so on. I mean, overall, you can see that the number of vertices is n. For example, if you had about if you set n to be 6 and 1, 2, 3, 4, 5, 6. So you have n for every n vertex such a polygon, then there are n/3 floor this teeth or prongs of the polygon. Now, wherever you place a camera to cover this triangle, so that camera cannot see this triangle. So to cover a point which is in this triangle and in this triangle, you have to keep separate cameras. So no camera can see the apex of this two distinct triangles. So this apex of this triangle and apex of this other triangle cannot be seen by one camera. So for every prong, you will need one camera. So n/3 by floor cameras are necessary for this simple polygon. Do you see that?
Yes.
Okay. So I think this is the art gallery theorem. I have shown you the art gallery theorem, and I want to thank you for coming. So this is a shorter session because we did not discuss the proof of that shifting strategy. So that shifting strategy is called the Habermas technique. It's not very easy to follow. But anyway, we can move to the next session. If you have any questions, doubts, feedback, anything that you think that there is some scope for improvement, you can let me know. I mean, I could not discuss that proof because I did not do a good job in making you understand. So I'll try to improve on that. Any suggestions? Like, can you give any suggestion on how I should have explained that proof so that it would have been more accessible?
Sir, maybe using some animations would have helped.
There was a lot of. Let's look at that slide again. Let's look at the slide once again. I created quite a few slides. Here, window, and covering this. So this was the last slide. Yeah, so you were saying that beyond this, you want to see some animations, or rather, you were saying that animations beyond this would have been helpful. So where exactly did you get lost?
Sir, I actually followed like whatever you told till the point you continued.
So you followed.
Yes,
Okay.
till the point you continued.
So let's, for your sake, I will complete the proof in next 10 minutes, let's say. You have time?
Yes, sir.
Okay, let's look at the proof then. Because there was no feedback, so I thought nobody's getting anything. So I said that if you have placed a grid and somebody has given you the optimal solution magically, and it turns out that none of the circles of the optimal solution intersect the grid boundaries. So the grids are 3 cross 3. Every grid is 3 cross 3. Then you must have done the best, because within every grid cell, you know how to find this optimal solution. Now, within every grid cell, if all the points are being covered by your optimal solution in such a way that the grid cell boundary is not intersected, then you must have done the best job. But if there is a circle in the optimal solution which is potentially able to cover points from multiple grid cells, then you may have taken more circles than necessary. Now we have to quantify that how much additional we may have taken. Okay. So we have to do this calculation. Okay. So let us do this calculation. So for 9 distinct positions of the grid, you have solved the problem 9 times. You have solved the problem 9 times, and you have output the best, output the minimum cardinality curve. Okay. So let us say, just I'm making it simpler. Just I thought of it now. Let us say that you reported that 15 circles are sufficient. You reported this 15 circles. So your minimum was 15. But you have solved it how many times? 9 times. Maybe once you got 16, once you got 20, once you got 21, and so on. You have got 9 numbers. Okay. But you reported the minimum. So we are going to find the average of these 9 numbers and argue that this average of these 9 numbers is at most 13 by 9 times OPT. That is what we are going to argue. And because average is this much, and you know the minimum you have reported, then what you have reported, the minimum is also at most 13 by 9 times OPT. That is the plan. So do you understand the plan?
Yes.
Okay. Then how do we find the average? So that is where we will do a transformation. So we have to count. So a transformation is what? The transformation is the following. That I'm going to look at the optimal solution. The optimal solution consists of some circles. Some circles. I do not know how to compute the optimal solution, but the optimal solution exists. And if somebody can show me the optimal solution, let us say, seeing the optimal solution is not necessary. We're just going to argue with respect to the optimal solution because it exists. So how many of these circles intersect the grid and how many of these circles are contained within the grid sets? So let us say the situation was like this. Yes, I have drawn a situation like this. I mean, this is hypothetical. So this thing is not there. Oh, so you have to make sure that the distance between the lines is 3. So some more gap is necessary. This much gap is necessary. So I want to check that how many are intersected and how many are within. That's what I want to check. So in this case, I can see everything is intersected. Okay, so but I will give it a shift. So once I give the shift, I don't know how to give the shift. Let's try. So let us give one shift. It's okay. It's not moving. Okay, yeah, it's moving. So once I give the shift, then some of the circles which are previously intersected now are within. Now this is the setup. Now see what happened. Okay, it's not easy to show this, but anyhow, so some of the circles which were earlier intersected are now inside. But I want to ask that for how many of these 9 distinct positions of the grid cell a given circle will get intersected? Is it all 9 or is it less than 1? Okay, so now we have to do a very clean job. We have to count that for a given circle in the optimum, out of the 9 distinct configurations of the grid cell, how many configurations are going to intersect it, and how many configurations will be such that the circle is completely contained within one of the grid cells. Now we have to do a very clean job. So the question I will write down. So how many configurations? For how many out of the 9 configurations of the grid cell, how many out of the 9, a given optimal circle will be intersected by the grid? That is the question we want to answer, and here we have to be very careful. Now look at this picture. So this is my picture. I have drawn a 3x3 grid cell, and this is a circle which has radius 1. Okay. Now, if this is the position of the grid cell, then the circle is not intersected by the grid boundary. But if there is a shift, to this position. So this guy moves here. Then the circle is intersected. The circle is here. It is intersected.
Yes, that makes sense.
Yes. Now, where else? If I shift up 1 unit, then this guy goes here. Again, there is an intersection with the circle. If I shift let's see, here here there is an intersection, here there is an intersection. If I put here, this guy goes what is the value of delta we have taken? 3. So 4/3 square. So it looks like that only one position. Okay, so yeah, so I think except this one position, all 9 positions are intersecting. So 8 out of 9 positions, there is going to be intersection. But if this circle was slightly here, what is the radius of the circle? The circle will touch. Touching will also consider it. No, fine. So let us say. So it is for a fact that one position is there definitely, which is non-intersecting with this circle. But 8 positions are intersecting. Fine. That is fine. So now I want to count this average. So what? So how many? So what is the average? That how many circles we have reported. So for every optimal circle, out of the 9 times we will run this algorithm. 8 times we may have to count twice. So 8 times we may have to count twice. So 9 times we will count once. So how we should put it? Optimal circle. 9 times it is contained within one grid cell, but 8 times we may have to count twice. So this thing divided by how many times we have iterated. So it comes out to be 17 by 19 OPT. So I said 13 by 9. It should be 17 by 9.
Sir, could you please elaborate on 8 times we have to compute twice? What's the twice part?
No, I think you are right. We have to be more careful. So once I move this thing here, okay, then this circle is part of this grid cell as well as this adjacent grid cell. So this circle get counted twice. So this is an optimal solution circle. And if it is contained within the grid cell, then we don't count it. If it is contained within, we count it once if it is within the grid cell. If it is shared by two grid cells, this is one grid cell, this is another grid cell, then we may have to count it twice. Again, if I move it here, we have to count it twice. Here again twice. Here again twice. Here, okay, so here it will be counted once for this grid cell, once for this grid cell, once for this grid cell, once for this. So at one position it will be counted 4 times, right? So I have to be more careful. At this position also it will be counted 4 times. So this grid cell, this grid cell, this grid cell, this grid cell. So there are 2 positions where it is counted 2 times. Here it is counted once. Here it is counted once, twice, 3 times, 4 times. So this position is also 4 times, this position is also 4 times, this position is also 4 times. So all these 4 positions which are inside the circle are 4 times. Okay. So you have to count more. So this factor will go slightly worse. So this position is 2 times because if you move this guy slightly up, then the circle is intersected, but the circle is part of only 2 grid cells, this one and this one, up and down.
Yes.
The same thing is going to be true for these other positions, like this position means those positions where the corner is outside the circle. There we're going to count twice, but for all these other 4 positions we have to count 4 times. So let us update what we said. So 9 into 1 time plus 8 positions 2 times plus remaining 4 positions 4 times. So additional again 2 into 4 OPT. So 4 positions, additional 2. So within this we have counted once for every circle. But within this we are counted additionally once for 8 circles. But now for all these 8 circles we have already counted twice. Now additionally for the 4 positions. Okay, let me say it once again. So there are 9 positions. So for every position we have counted once here. But then we realize that we have to count twice for additionally 8 times. But by now we have already counted twice for this additional 8. But out of this additional 8, there are 4 where we should count 4 times. So again, additional 2 times. Give it a thought. So 8, 8, 16 and 9, 27. So that is how it is 3 OPT. So I should write. So we have come down to 3 factor from 4 factor. But the point is, okay, let's ask. So do you understand what has happened? I think there could be some doubts. This counting is, yeah, it will require more thought for you.
Yes, the basic idea was clear. I think I will just have to work some of it myself to fully
I will
convince myself.
share the reference with you, with all of you. So the point is, if instead of a 3x3 setting, if we make it a 9x9 setting, like if we increase the grid cell sizes, then we can get it down to even smaller factors. So this can in fact become very close to optimal, 1 plus epsilon of OPT. And if we get a solution which is very close to optimal, so epsilon is any constant greater than 0. So if we can get down to very close to OPT, but not really OPT, then that kind of an algorithm is called a PTAS. So this algorithm is a PTAS for a very large grid cell. So what is a PTAS? It's a polynomial time approximation scheme.
Sir, I noticed that it's written 1 plus epsilon. So it seems like, does the user have some control to what epsilon he or she
Yes.
wants?
So epsilon depends on the grid cell size that you choose. So you as an user or as an algorithm designer can choose the grid cell size. So I choose the grid cell size to be 3x3. So you can choose it to be, so generally people choose it 1 by epsilon square, cross 1 by epsilon square. Then it turns out to be a 1 plus epsilon approximation. So what it means is the following. So suppose you want, let us just be crude and say that you want a 1.1 approximation. Then you will put epsilon is equal to 0.1. Then you have to take a grid cell of size 100 cross 100. Right?
Right.
So to achieve 1.1 approximation, you need a 100 cross 100 grid cell. I mean, I will share the reference material with you. There is more to it. Maybe I should have drawn some figures. Now I realize that okay, these things also could have been explained with some figures. There is lack of time. We're doing it every day. So anyway, I'll see you tomorrow. So tomorrow we'll talk about packing questions, and tomorrow will be the conclusion. And I hope to see you again tomorrow. You have been very regular, so thank you for coming every day. Yeah, if you have any other questions, you can ask me. Otherwise, we can conclude early today. Thank you, Mandana. Fine, fine. So let us stop recording. I'll see you tomorrow again.
Thank you, sir.
Thank you.
Thank you.
Thank you, Krishna.